Slides now?
Yeah, see the slides, but we also see the. Okay, perfect. Everything is great. So I'm very happy to introduce Dachman-Soled, who's going to give the last talk of the day and talk about new techniques for zero knowledge.
Okay, great. Thank you so much. So I'm going to be talking about new techniques for zero knowledge, leveraging inefficient provers to reduce assumptions, interaction, and trust. And this is joint work with Marshall Ball, who may be there, I'm not sure. And sorry, it's really hard to see anyone. And Mukul Kulkarni. Okay, so I assume everyone here knows about NIZKs, and also I know the last talk was about NIZKs, so I won't actually define NIZKs, but I will talk just a little bit about the landscape of NIZKs for NP, because there's like a lot of moving parts here, and it's going to be a little bit important to keep track of the different parameters. So there's various things that we can look at. We can look at whether the honest prover is efficient or inefficient. We can look at whether the soundness guarantee is either computational or statistical. We can look at whether the zero knowledge guarantee is computational or statistical. And we know that we need some kind of setup, and we're going to be considering essentially two different types of setups. So a uniform reference string where the shared bits are just chosen uniformly at random, as well as a common reference string where they can be chosen from some other distribution. So let's just see a few examples of what is known to be achievable. And I apologize if I skip out any related work. There's an awful lot of work on NIZK, so feel free to add if I missed anything. So let's first look at the regime where the honest prover is efficient. And for now, let's look at statistical soundness, computational zero knowledge, and a common reference string. So in this case, we have several different constructions from various assumptions. And you can see that I put the assumptions here in the box. And this box is going to be red to kind of indicate bad. And it's not really bad, but it's going to be bad in the sense that all of the assumptions that I've listed there are all known to imply public key encryption. And later on, we're going to be looking at assumptions that are weaker than that. Okay, so what else can we do? Well, we may also not really want a common reference string. It's a little bit preferable to have a uniform reference string. In that case, you can use like maybe the NIST beacon, or maybe even like a natural phenomenon and two-source extractor to kind of generate your uniform reference string. So that in some sense like reduces the amount of trust that you're going to need. And in this case, we have like lots of assumptions that we know, lots of constructions that we can get this from. But again, you'll notice that this box is still all red. So these are all assumptions that imply public key encryption. If we switch the soundness and the zero knowledge, so computational zero knowledge and statistical zero knowledge and computational soundness, we also know constructions, both in the common reference string and in the uniform reference string model. So this is all great, but what we wanted to look in this talk is like reducing assumptions. So one way that we can try to reduce these assumptions is to actually allow, instead of having an efficient honest prover, we can allow the honest prover to be inefficient. And now we're again going to want to have statistical soundness and computational zero knowledge. And in this case, we have constructions in the common reference string model from the kind of minimal assumption of one-way functions. So now this box is green because we're able to construct this primitive from these weaker assumptions. And if we want a uniform reference string, which we said like in some sense reduces the trust, then we can still do it. And we can still do it from these green box assumptions. But now in the plain model, we only know how to do this from one-way permutation. instead of one-way function. And the talk that we just heard was on how to actually achieve this in the random oracle model, in which case there actually is no need for a uniform reference string at all. I just want to point out an inherent property that's going to be coming up in the talk is that when we look at these inefficient honest prover and these proof techniques that we have, kind of a main feature of this, the main property of these constructions is that the honest prover is going to run in time larger than what we allow the zero knowledge distinguisher to run in. And if you remember kind of the implementation of the hidden bits model, this is kind of the reason why, because the honest prover has to be able to open the hidden bits, but the zero knowledge property relies on the fact that the bits that weren't open remain hidden. Okay, so now I'm going to move on from that, and I'm going to talk about a slightly different primitive, but very related, called ZAPs. And again, I'm going to be looking at ZAPs for all of NP. The short description of a ZAP is that it's a two-message witness indistinguishable public coin protocol for proving that X is in an NP language. The first message from the verifier to the prover is just going to consist of a bunch of random bits. So we're going to call it row. And the message going from the prover to the verifier is the actual proof pi. And we have the completeness, soundness, and witness indistinguishability properties. And I just want to emphasize for soundness, we actually have statistical soundness, which says that with high probability over row, and for a statement X, which is not in the language, there doesn't exist a response pi, which is going to cause the verifier to accept. Whereas for witness indistinguishability, we're going to have a computational property, which says that for all first messages row, we can actually just fix the first message. The distribution on the proof pi, when the prover has input XW versus XW prime, so these are two witnesses for the same statement, are computationally indistinguishable even given both the witnesses. And I also want to note that since we've been talking about inefficient provers, the notion of ZAPs becomes trivial if either the witness is unique, so if there's only a single witness for the statement X, or if we allow the prover to be completely arbitrarily inefficient, in which case, like given a statement in the language, it can always just look for the canonical witness and send a proof based on this canonical witness. Okay, so what do we know about the relationship between NIZKs and ZAPs? So the seminal paper that introduced ZAPs by Dwork and Naor also showed a construction, and they showed that assuming the existence of a NIZK proof system for a language L with efficient provers in the uniform random string model, there exists a ZAP for language L with efficient provers. And we're going to be looking kind of a little closely at this transformation in this talk. And we're going to see that in order for the security reduction to work, in order for the security for the computational witness indistinguishability argument to work, the honest prover has to run in time less than the allowed runtime of the zero knowledge distinguisher. And so using this theorem of Dwork and Naor, we actually have an equivalence that goes both ways. So NIZK in the URS model implies ZAPs, and ZAPs plus one-way function also imply NIZK in the URS model using the FLS technique. And this is all only for the case of efficient provers. Okay, so basically, if we want to construct ZAPs with efficient provers, and we want to construct it from these green assumptions, these mini crypt assumptions that do not imply public key encryption, We're kind of a little bit dead if we use efficient provers because we know that these two notions are actually equivalent. And so since we don't know any construction of NIZK with efficient provers from these mini crypt assumptions, we're also not going to be able to construct ZAPs. So the question that we kind of motivated us was we were asking, like, if we relax the assumption on efficient provers, can we actually get meaningful notions of these ZAPs from mini crypt assumptions? And for purposes of this talk, I'm going to assume that these are assumptions that are known to be separated from key agreement and hence also from public key encryption. And the problem, as you might have noticed, is that in the known NIZK constructions from mini crypt assumptions, the honest prover has to run in time greater than the allowed runtime of the zero knowledge distinguisher. And this kind of contradicts the property that we needed in order for the Dworkin or security reduction to go through. So in this work, we tried to get around that. And what we did is we showed that assuming the existence of a NIZK proof system for a language L with provers running in time T in the URS model, there exists a ZAP for L with provers running in time poly n times T, where n is security parameter. So we were able to get around this drawback of the original Dworkin or construction. And note that in our theorem, there is no restriction on how T relates to the allowed runtime of the zero knowledge distinguisher. However, note that the theorem is vacuous if T is enough time to find all witnesses, because in that case, we have unconditional ZAPs. And a corollary of this theorem is that assuming one-way permutations, there exists ZAPs for NP with sub-exponential time provers. So we can get ZAPs for all of NP without having these trivial provers that can break every NP language. Another advantage of constructing ZAPs is that we can try to further reduce the trust and further reduce the interaction. So what if we just fully want to get rid of the URS and also get rid of the two messages in the ZAP? Well, it turns out that we can leverage a result of Barak, Ong, and Varan to show that assuming one-way permutations and hitting set generators for code non-deterministic circuits, there exists non-interactive witness indistinguishable proofs, NIWI for NP with sub-exponential time provers. So we can actually change the two-message protocol into just a one-message protocol. And we can also go one step further, and if we assume the above as well as sub-exponential secure uniform collision-resistant hash functions, then we can get some kind of notion of offline NIZK in the no setup model. So we don't need any setup at all, where the simulator this notion says that the simulator is efficient after a pre-processing stage and before seeing the statement. However, the entire simulator is not polynomial time. Okay, so those are the results. And for the rest of the talk, I'm going to recap the Dworkin or transformation, which I assume many people are probably familiar with. And then we'll see the issue with having an inefficient honest prover algorithm. And then we'll get around that. We'll present a new construction. And then I'm guessing I won't have time, but if there's time, I'll also discuss a new definition of fine-grained NIZK that we introduced in this work, as well as observing that our transformation also works in the fine-grained setting. And then finally, I'll wrap up with future directions. Okay, so the initial transformation of Dworkin Naor, it starts with a NIZK in the URS model, and it's trying to construct a ZAP. And what the construction is going to do is the verifier is going to send a sequence of random bits to the prover. And the total number of bits that it's going to send is n prime times n, where n is the length of the uniform random string in the NIZK construction. And n prime is like the number of times that we're going to repeat this construction in parallel. And what the prover is allowed to do is the prover is actually allowed to choose its own random string of length n. It can choose it, it's supposed to choose it at random, but it can choose it however it wants. And it's going to XOR this random string block by block into the n prime blocks that were sent by the verifier. And once it XORs those, it's going to get these purple blocks here. And each of these purple blocks can be viewed as a URS for the NIZK. And then the prover is just going to send the corresponding proofs, pi1 to pi n prime, for each of these different URSs. And then the verifier will check that all of these proofs verify, and if all of them verify, will output 1, otherwise output 0. So how does this transformation work? So how do they argue soundness? So to argue soundness, they note that if you fix these red bits of the prover, then the probability over messages of the verifier, which are just random strings, that all of the URSs are bad, is going to be epsilon to the n prime, where epsilon is the failure probability of a single run of the NIZK. And so by union bound, the probability that all of these purple URSs are bad for any choice of red bits is going to be at most 2 to the n times epsilon to the n prime. And choosing n prime sufficiently large is going to make this negligible. Okay, so that's how they prove soundness. How do they prove witness indistinguishability? So this is going to be by a hybrid argument. And in this case, it's going to go one at a time through the n prime number of proofs. And in the ith hybrid, the ith proof is going to be switched from an honest proof with witness W1 to a simulated proof, and then back to an honest proof with witness W2. And the indistinguishability of consecutive hybrids is going to follow from a reduction to the zero knowledge of the underlying NIZK. So how exactly is the reduction going to work? So the reduction is going to get as input a simulated proof with CRS tilde and pi tilde, and it needs to program the ith block of the CRS, the ith purple block of the CRS, to be equal to this inputted CRS, which is this pink block. So how is the reduction going to do that? So the reduction is going to actually choose these red bits of the prover in such a way that when you XOR the ith blue block of the verifier with these red bits, you actually get exactly this pink CRS string. And then for that position, the prover can also just send the pi tilde that it got from the as input. And then for all of the other blocks, it's just going to run the honest prover strategy. Okay, so what is the problem with inefficient provers? Well, the problem is this part over here in red. So running the honest prover strategy with respect to the purple CRS for all the other blocks. So this is no longer going to be efficient. And in fact, the honest prover strategy is going to have a longer runtime than the allowed zero knowledge distinguisher in the constructions that we have. Okay, so you cannot just run the honest prover and then still get a reduction to the zero knowledge property. So what can we do to try to fix this? So one attempt is to just try to provide all the proofs for the other blocks as non-uniform advice. So the reduction is going to get all the proofs except for the ith block as non-uniform advice. And then the ith block is going to get programmed to match the pink CRS and pi tilde that it got as input. However, that is not quite going to work. And the reason is that we cannot just provide all the proofs as non-uniform advice because we actually don't know the other purple strings. We don't know the other CRSs ahead of time. And the reason is that even if we fix the first message of the verifier, even if we fix all of these blue bits, the red bits chosen by the prover are going to depend on this pink CRS that we get as input. So only at the time that the reduction actually gets its input, which is CRS tilde pi tilde, only at that time can we actually compute this red string of the prover. And only once we compute this red string of the prover, even if the first message of the verifier is fixed, only then do we learn the CRSs of all the other positions. So there doesn't seem to be a way to just hard code this information into the prover or into the reduction. So another attempt can be to try to somehow make the different blocks of the proof independent. So the property that we seem to need is that for every I, the ith block of the purple string should be independent of all the other blocks. And this will let us fix all the other blocks and then program the ith block of the purple string when we get our input. But if we do this, it's actually going to give the prover too much freedom. So the prover will be able to choose too many of these random bits. And then this is going to actually break the soundness argument from before. So the solution that we showed is that we showed that, in fact, we don't need full independence across these purple blocks in order to make the proof work. We just need to show a type of almost pairwise independence property. So we just have to show that for every pair of blocks, the dependency across these blocks is small. Okay, so how do we do that? How do we get a situation where the dependency across the blocks is small, but the prover doesn't have enough freedom to break soundness? So the main tool that we're going to use is a design which was introduced in the famous hardness versus randomness paper of Nisan-Wigderson. A design is going to consist of a universe of elements. So in this case, L is the size of the universe. And the design is going to allow you to construct n prime number of sets where each set has size n. And the overlap, the intersection between any pair of sets is at most C. And what we can do with this, different parameters are known, but for us, it's going to be good enough to construct designs with universe size L equal n squared for constant C and for n prime, so the number of sets is equal to n to the C. And the key property that we're going to need from the designs for soundness is that the total universe size L is a lot smaller than n prime. So if you just naively try to construct these, you can split up your universe L into sets of size n by creating a partition. But in that case, your n prime will be smaller than L. So the key property of these designs is that the universe L is a lot smaller than n prime. And for the reduction to be able to succeed, for the computational zero knowledge property to work, or computational witness indistinguishability property to work, what we need is that the overlap between any of these two sets is small. Okay, so let's see how we will plug this into our construction. So it's going to look very similar. So the verifier is going to be sending a random string to the prover. Each of the random strings is length, each block of the random string is length n, where n is the length of the URS in the underlying NIZK. And we're still going to be sending n prime of these sets. But now we're going to set parameters differently. So we're going to choose a design, which is this like grid over here that or the universe of the design is this grid that the prover has over here. And the universe size in this example is 16. The set size n is 6, and the intersection size c is 2. And the number of sets that we're going to be constructing n prime is 6. And now what we're going to do is the prover is not just going to XOR its entire grid into the random string sent by the verifier. It's actually going to choose which bits to XOR into each of the n prime CRSs according to the sets of the design. So these red and yellow bits are the first two sets of the design. Then we have a green set, a purple set, a light blue set, and a yellow set. And then once we've XORed each of these, so the prover is going to choose the bits corresponding to the entire universe L, and then it's going to XOR them into the string sent by the verifier, and it's going to get n prime different CRSs. And then for each of the CRSs, it's going to use the prover from the underlying NIZK to generate a proof, and it will send all those proofs over to the verifier. And the verifier will verify all of them. If they all accept, it will output 1, otherwise output 0. So how are we going to argue soundness? So in this case, the prover has more freedom. The prover can choose 16 different random bits. But if we fix the random bits that the prover chooses, the probability over the first message of the verifier that all the CRSs are bad is going to be epsilon to the n prime, just like before. And now, again, we're going to take a union bound, but now we're taking a union bound over 2 to the L different things. And we're still going to be able to make this work because the properties of the design are that the size of the universe L is actually a lot smaller, can be a lot smaller than n prime. And so parameters can be set to make this negligible. On the other hand, we're now going to be able to argue witness indistinguishability, even though we have inefficient provers. So how is this going to work? So we're going to do a similar hybrid argument as before. And in the ith hybrid, we're going to assume right now that we're switching this last proof here from some witness W1 to another witness W2. And what we're going to be able to do now is we're going to actually fix the bits corresponding to the entire universe of this design. We're going to fix everything except for the yellow ones, because the yellow ones are the set that corresponds to this last, this final proof over here. And the property of the design tells us that once we fix the first message of the verifier, for each of the n prime blocks corresponding to the n prime different CRSs, there is actually, in this example, there's only 2 bits that are unknown. So after you fix everything except for the yellow bits, there is only 2 blocks that are unknown in each CRS. So for example, in this red string, there is actually only 2 bits of this red string that intersect with the yellow string. And so in the pre-processing stage, in the non-uniform advice, everything can be known except for these 2 yellow bits. Okay, and in general, you won't necessarily have 2, but you'll have some constant C number of unknown bits. So why is this good? So what this is going to allow us to do is that in the non-uniform advice, we're actually going to pre-process 4 different possible honest proofs for each of the blocks, corresponding to the setting of the bits that intersect with the yellow set. So for example, in this first red set, we're going to assume the CRS can be one of 4 things. And for each of those 4 things, we're going to pre-process a proof and then hardwire it into the circuit of the reduction. Okay, and so now in the online phase, so that was all in the pre-processing phase. In the online phase, the reduction is going to actually get its input, which is CRS tilde pi tilde, and it needs to program the ICRS to be equal to the pink value. In order to do that, it's going to have to set these yellow bits, and that is then going to set at most 2 bits of each of the other CRSs. And now we can just use those 2 bits that we just set in order to select the correct 1 out of 4 honest proofs for each of the blocks. Okay, so that's basically the construction. So we were able to push all of the inefficient, everything the inefficient prover had to do, we were able to push into the pre-processing stage, except for doing this selection of 1 out of 4 proofs, or 1 out of 2 to the C proofs, given the C bits of the CRS that are revealed during the online stage. Okay, so it turns out that not only do we get an efficient reduction, a polytime reduction, but actually the reduction in each hybrid step is an NC0 circuit plus running the distinguisher for the NIZK. So that means that given distinguisher for witness indistinguishability for the ZAP. So that means that given a WI distinguisher in certain circuit class F, we obtain a NIZK distinguisher in class F composed with NC0. Okay, so I guess I probably have enough time to discuss the fine-grained NIZK. So in the paper, we also considered a fine-grained regime. So right now, I've been talking about polytime verifiers and super polynomial provers. But we also considered a fine-grained NIZK regime, and kind of the cliff notes of this definition is that now the prover is polytime, but the verifier, the zero-knowledge simulator, and the zero-knowledge distinguisher are all going to be in some smaller circuit class F. Yeah, I guess that's what this definition says in symbols. So we have indistinguishability against circuits in F from these 2 distributions, where the first distribution is the honest generation of the URS and the honest generation of the proof. And the second distribution is a generation of a URS and a proof by a simulator, and the simulator itself is in this circuit class F. Okay, and now we can observe that our transformation from before also works in the fine-grained setting. And so I didn't define it, but it can be used to achieve a certain notion of fine-grained ZAPs that we also introduced. So given a NIZK verifier circuit, the verifier circuit of the ZAP that we constructed basically just runs the verifier in parallel and takes an AND. And given a witness indistinguishability distinguisher circuit for the ZAP, we saw that the reduction constructs a distinguishing circuit for the NIZK that is basically just the witness indistinguishability circuit composed with C prime, where C prime is an NC0 circuit. So we can instantiate this transformation from fine-grained NIZK to fine-grained ZAP for the case of NC1. So assuming that pi is an NC1 fine-grained non-adaptive NIZK proof system in the URS model, then our transformation is going to yield and NC1 fine-grained ZAP. Okay, so I guess I'll finish up with future directions. So one question is just whether this design-based technique can be useful for other interactive protocols or other settings where we have parallel repetition. It seems like it can maybe be used to avoid complexity leveraging or just somehow make the reduction more efficient than if you don't have this technique. And then this relates to kind of higher level complexity questions. So we have this notion of ZAPs with sub-exponential time provers, but actually we don't know a lot about how it relates to other primitives. So for example, we don't know whether the other direction holds. So do ZAPs with sub-exponential time provers and one-way function imply NIZK in the URS model with inefficient provers? So this implication holds with efficient provers, but not clear what happens with inefficient provers because the FLS paradigm doesn't seem to help here. So the FLS paradigm adds kind of a trapdoor witness and the simulator runs an honest prover with respect to the trapdoor witness. But in our case, the honest prover is inefficient. And so this would give you an inefficient simulator. And then I guess another question relating to also the last talk before this is, can ZAPs for NP with sub-exponential time provers be constructed from one-way function? So we can get it from one-way permutation. We don't know how to get it from one-way function. If we got NIZK in the URS model from one-way function, then it would immediately, using our transformation, also imply ZAPs. However, due to the above, it seems like ZAPs in this inefficient prover regime may be weaker than NIZK in the URS model. So it might actually be easier to attack this question and try to construct these ZAPs for NP with inefficient provers from one-way function. Okay, so that's all I've got, and happy to take any questions.
Perfect timing. Questions, Dana? Okay, let's thank Dana again. And now for everybody who's in the room,